So at the end of our last video, we had talked about the third ionization energy of magnesium, and we wrote this equation here where we said, well, the third ionization is when you take magnesium that's already lost 2 electrons and it loses 1 more to become magnesium 3+, and there's that extra electron that's now lost. And we predicted that the ionization energy, kind of based on these numbers right here, we basically predicted it'd be around 2100, maybe 2200. Okay, now if we scroll down here, we see a table here that actually shows the different ionization energies. 1, 2, the third ionization energy, the fourth, etc. Notice that with magnesium, the first 2 are the 2 that we had up there, 738 and 1450. But notice, remember what our prediction was. Our prediction was around 2100, maybe 2200. But notice that the real third ionization energy of magnesium is 7730, which is way, way higher than our predicted 2100. Even if we predicted, well, every time it's going to double, well, then it would have gone from around 700 to 1400 to maybe even 2800 if it doubles. But even so, it went way, way higher than even that. It went from 1,400 to over almost 8,000. Okay, so the question is why? Well, let's look at magnesium. Magnesium has 12 protons in the nucleus. And yes, it also has 12 neutrons. We're not too worried about that. And then let's think about the electrons. It's got 2 electrons in the 1s subshell. So 1s2. So there's our first shell. And then in the second shell, we have 2s2, 2p6. So there's 8 electrons in that second shell all total, right? The 2 and the 6. And then in the third shell, there's 3s2. So when you take electrons away, remember we learned about this earlier when we talked about removing electrons from ions. When you do that, when you take electrons away, you take them away from the furthest shell from the nucleus. So the first electron that gets taken away is, of course, one of these. So for this first ionization energy right here, that's 738, we're taking away this electron, one of those electrons right there. So now it becomes 3s1. So now we've got Mg+. Okay, now we're going to take another electron away. So now we're to the second ionization energy. So now we've got 3s1. So now that whole 3s shell is completely gone. Now we're at magnesium 2+. So we've lost 2 electrons. And the electrons that we lost were what we call the valence electrons. And we've heard that term already. Okay, and the valence electrons are the electrons that are in that last shell. And now we've removed all of them. So now the question is, what's the next electron we're going to take away? And the next electron we're going to take away is of course, here in the second shell, and it's in the 2p subshell. And we know that the 2p subshell is way, way closer to the nucleus. And there's less, like right now out here in these 3s electrons, 3s1 and 3s2, all these electrons here are basically kind of blocking these electrons out here. They're blocking that attractive force of the nucleus. Okay, well now those electrons aren't there anymore. So these electrons, these second shell electrons, are much, much closer to the nucleus because they're in the second shell, not the third shell. And there's less electrons blocking that attractive force. And so what happens is when you go from, what were these electrons called again? The valence electrons. When you jump from, when all of those valence electrons have run out, when you've taken all of those valence electrons away and you start to take away these electrons, these are called the inner shell electrons. Once you start to take away the inner shell electrons, what you find is you find a very, very big jump in the ionization energy. And you'll notice here on this table that that's what happens, is all of these first blue ones here, in the white section, all of those are the valence electrons. And once all of those get taken away, now you're in the, as you can see right here, the inner shell electrons. Okay? Now, what that does is it kind of helps us to identify elements sometimes. So here in this paragraph right here, I kind of just explained what I already explained above. The next electron has to be removed from the 2p subshell. That, again, is much closer to the nucleus. That's how you're going to explain it on a test, and has less electrons blocking or shielding the attractive force of the nucleus. That's the things I'm going to be looking for when you answer a question about this. So notice that anytime you go from a valence electron to an inner shell electron, there's a big jump in the ionization energy. And what that does is it helps us to identify an element. And let me explain to you what that means. Okay? Let's look at example 1 here. It says an element in the second period of the periodic table. So let's make sure we understand what that means. If I have my periodic table here, the second period, so the first period, again, starts here at hydrogen and goes across. The second period, therefore, is lithium all the way over to neon. The third period is sodium to argon. Fourth period, fifth period. It just goes down 1, 2, 3, 4, 5, 6, 7. Okay, so the second period, again, is lithium to neon. So it says an element in the second period, so again, anywhere from lithium to neon, has the following ionization energy data. The first ionization energy is 1,000. The second is 2,000. The third is 4,000. And again, I'm not saying the whole number. The fourth is 6,000. The fifth is 37,000. And the sixth is 47,000. Okay, and then it says identify the element. Okay, so notice that as you take electrons away, it gets progressively more difficult. It requires more energy to take the next electrons away. But what we're looking for here is we're looking for the big jump. Where does it go from taking those electrons, remember up here, where does it go from taking valence electrons away to moving in to the inner shell electrons? That's what we're looking for. So where do you see the biggest jump in ionization energy? Okay, well, 1,000 to 2,000, that doubles. 2,000 to 4,000, that about doubles. 4,000 to 6,000 goes up about, not even doubling. 6,000 to 37,000, though, goes up by about times 5. Whew, that's a pretty big jump. And then here it doesn't even double. Okay, so where's our big jump? Our big jump happens between the fourth and the fifth. And what that tells you, again, is that 4 electrons can get lost fairly easily. But then that fifth one now is an inner shell electron. Now it's one of these electrons. So how do we know what element it is? Well, now we go back to the periodic table and we just look and we go, oh, what's the only element in period 2 that has 4 valence electrons? Because remember, 4 electrons could get taken away fairly easy. So I look at my periodic table and I go, oh, lithium 1, beryllium has 2, boron has 3, and carbon has 4. So therefore that we know that this element must be carbon, because the only element in period 2 that has 4 valence electrons is carbon. Okay, and again, I explained that. Maybe read that, and that will hopefully help you understand that. Okay, example number 2 says an element in period 4 has the following ionization energy data. So again, we're in period 4 now. So where are we looking? We're looking at potassium all the way over to krypton. Now forget the D subshell again. Whenever we talk about ionization energy, we're not talking about the D subshell. So we're just talking about potassium to calcium and then gallium over to krypton. So question being here, where do you see the biggest jump? So 598 to 1100 is about doubling. 1100 to almost 5,000 goes up by a factor of 5. Not even close to doubling, not even close to doubling. So the biggest jump is from the second to the third. So again, what does that tell me? It tells me that this atom can lose 2 electrons fairly easy. And what are those electrons that it loses fairly easy? The valence electrons. But then the next electron to be removed must be an inner shell electron. So what is the only element in period 4 that has 2 valence electrons? Is calcium. Okay, so I've identified the element. I've said it's calcium, and how do I know that it's calcium? Okay, it's calcium because the big jump occurs between, and hopefully you're writing this down too, guys, between the second and the third ionization energy. Meaning that calcium has 2 valence electrons and the third must be an inner shell electron. Okay? So talk about why that big jump between the second and the third is important, because if the big jump happens between the second and the third, that tells you that the element must have 2 valence electrons. And calcium, again, is the only one that has 2 valence electrons. The third one and the fourth one and the fifth one must all be those inner shell electrons. All right, let's practice this a little bit on Canvas. This is it for the video.